In this video, we are going to review average angular acceleration and instantaneous angular acceleration. So average angular acceleration, ang iyahang symbol is alpha sub AVG. Its SI unit is radians per second squared. And it is the ratio of a rotating object's change in angular velocity to its time interval. And its formula is delta omega over delta t. If you've seen my previous video, we talked about rate of change. And in this case, for angular acceleration, what rate of change are we talking about? So we're still talking about the rate of change. And in this case, we are interested in the change in angular velocity. So if we draw a graph again, omega versus time, for some initial time, we have some sort of initial angular velocity, and we're trying to quantify the change in angular velocity. Maybe nagpaspas siya, so maybe na siya sa taas, right? And that has a corresponding time final as well. Okay, so not only are we interested in the change, okay, there's definitely a change here, ni Saka siya, but the rate of change. So unsa siya kapaspas ni Saka? Thus, there is a delta time at the bottom, which is very important part of the definition of average angular acceleration. So it's a rate of change in angular velocity. Let's go to some example. A rotating object's angular velocity is found to be a function of time given by that expression where t is in seconds and omega is in radians per second. What is the average angular acceleration of the object from t equals 0 to t equals 3 seconds? So average angular acceleration is alpha AVG, and ang pasabot daw ani is at t equals 0 to t equals 3 in an omega versus time graph, trying to figure out the of rate of change of angular velocity. So maybe our omega initial is right here, I don't know, and our omega final is right here. So we're trying to figure out how much and how fast did this omega change from initial to final. Well, we do know our t initial, which is 0, and our t final, which is 3. Do we know our omega initial and our omega final? By the way, if you want to answer this problem on your own, you can pause for and then solve it in your notebook and check later. But atong problema karon is we do have the formula. Sorry, I feel sick. Oh, right. We have this formula, but we only know TF and TI for now. What is omega F and omega I? Well, omega F is just the angular velocity at TF, and omega I is just the angular velocity at TI. And our scientist has discovered this empirical formula relating omega F, omega and T. So, igo lang nato i-substitute. Again, this is similar to the previous video. So, for TF equals 3, substitute 3 here, we get omega F. For Ti equals 0, substitute 0 here, we get omega 0. And we already did omega 0. This is our omega I. And our omega, this is 3, is equal to 49.5 na ni siya. That's our omega F. And now it's just a matter of substituting. And we find that the average angular acceleration is 16.5 radians per second squared. How about instantaneous angular acceleration? So the symbol is alpha na lang, wala na tong AVG sa ubos, and SI unit is still radians per second squared. And its When we talk about angular acceleration, wow, it's a straight line. We mean instantaneous angular acceleration. It's again a rate of change, but a rate of change at an instant of time. And again, we derive omega dt. This is the derivative, right? The derivative is the rate of change, or the slope of a tangent line. And we need a tangent line because we're looking at an instant of time. And a tangent line is a line that touches the curve at one point in time. Something like that. Anyway, let's look at an example. A rotating object's angular position is found to be a function of time given by theta t is equal to 0.5 t cubed plus 4t squared. What is the angular acceleration of the object? So we know that the angular acceleration is a derivative of angular velocity with respect to time, where our omega should be a function of time. So do we have that? Do we have omega as a function of time? Well, unfortunately, no. We only have theta as a function of time. So we have to do something about this. We have to convert this into an omega as a function of time. How do we do that? Well, first we have to derive this expression. It's a two-step process. We have to derive this as a function of time. So we have to solve for d theta dt to get omega as a function of time. So let's derive this, okay? Here, our rules for derivatives. Constant multiple rule, you just copy that. And the 3, itong ibalin sa coefficient. And t, we copy. And 3 minus na itong isa, that's the rule, just plus. And we copy the constant multiple. And our 2, which is the power, to follow the power rule, we bring the 2 down to the coefficient, copy the variable, and the original power, we minus 1. So 0 0.5 times 3 is 1.5. T squared plus 4 times 2 is 8, and t to the 1 is just t. This is our expression omega as a function of time. But if we're interested in acceleration as a function of time, we have to derive this again. So it's a second order derivative of this original function. So kaduha siya gi-derive, no? It's easy, it's all good. And if we derive, as you can see, ang 2 ginaog. Ang 2 na original power kinahimong 1. And ang 8t to the 1 man siya. But ginaog ang 1. And ang 1 nahimong 0. 1 minus 1. So t to the 0 is 1. So 8 times 1 times 1 equals 8. So basically, 3t plus 8. We now have an angular acceleration as a function of time that is 3t plus 8. And ato pa ba ning i-derive? Dili na. Because makuha naman nato ang angular acceleration if we substitute 2 seconds and we get 14 radians per second squared.